This is a fourth lab in the Advanced Control Series, Temperature Control Lab D. We're going to be taking a different approach in this lab. Instead of fitting to first principles energy balance, we're going to do system identification where we use an empirical model, such as this one, a second order system, or even just a first order system, such as the one shown just above. So let's go ahead and get started. We're going to go ahead and just get some of the data and then look at that data. Okay, so whenever you're pulling in data, the first thing you want to do is maybe visualize it. Just take a look for any outliers or bad data in the data set. So if you come over to Arduino Lab, we can go to Lab D, select that link, and that will bring you to these exercises. The very first thing that you want to do is just start collecting data or retrieve some of the data. So if you look at this link right at the top, this is going to be some data that you can look at. Let's go ahead and import this into Python and just take a look at it. So we're going to import matplotlib, okay, and pandas as well. We'll retrieve the data file. This is from the URL that you see right at the top here. It's just this URL. Okay, and then what we want to do is just read the CSV with pandas, and then we'll look at the header of it, the tail of it, the end of the data, and we'll also describe the data. We'll just do some basic statistics on the data. Okay, and then we'll generate a figure with a first subplot just for the temperatures, and we'll use the data columns for time and T1. Okay, let me just go ahead and look at those. Okay, make those red, and then blue X's for T2, and give it a Y label and a legend. And then the second subplot, and we'll do this with the heater 1, the heater 2, and give it a Y and X label and a legend, and then show it. Okay, so let's go ahead and just run this one and just take a look at our data. And so if we come over to view data, I'll just run this with IDLE, but you can run it with any Python distribution. Okay, and then we're going to get some summary statistics after it finishes importing, and then we'll get our plots. Okay, so here you can see the header, it just imported it. There you can see the last few rows, the last 5 rows, and then these are some of the statistics. Okay, the mean count, mean, standard deviation, min, and then the quartiles. Okay, and then the important thing here is just going to the data. You look for any outliers or anything that might cause a problem for your identification. So I think we're ready at this point. I'm also going to start the collection of step data. Go ahead and get my own data. If you have your own temperature control lab device, I would recommend just generating your own data. And we're just going to import a couple packages to do this. And then we'll create a file name with some heater steps. You can adjust these if you like. And for heater 1 and heater 2. And we'll connect to the Arduino. From this command right here, we'll open up a file name and give it a header. And then we'll step through for 10 minutes, set the heater values that we had defined right up here. We'll print those on a line, we'll wait 1 second, and then we'll do it all over again until we get to 10 minutes, and then we'll close the connection to the Arduino. And then we'll read that data file and then just plot it again. Okay, so there's our step data, and I'll get this one started. It'll pop up once it's done. Hopefully we'll have a new data file that we can look at. Okay, so it's going to just connect to the Arduino, and there you will see the summary statistics printing. I'll go ahead and minimize this. So let's get over to creating our gecko model and just doing this estimation based on the data. So we're going to import a couple of these packages like we saw before. If you don't have gecko, you can always do pip install gecko, and we'll get pandas as well. So we'll import the data. Either we have our own data file available, so once this finishes running, it will have our own data file, or we're going to go ahead and get it from this internet source. If you don't have a temperature control lab device, you can just import it here. Okay, we're going to go ahead and parse out some of the values. into just get the values of them instead of as data frames from pandas. Okay, so we're just going to parse out those 4 columns, and then we'll create the gecko model. And if you have a Windows or Linux or ARM processor, you can set this to false and solve it locally without an internet connection. Okay, we'll have our time. We're just going to load that in as a gecko parameter. These are the times where we want to be able to simulate. We're going to come up with some parameters that we're going to estimate. So let's talk about this. I'm going to put this side by side with our model here, and let's go ahead and just bring both of these up, so as we're talking about the model we can build it and explain just a little bit more about what's happening here. Okay, I'll put this over to the side. Okay, so for this empirical estimation, what we're doing is we're fitting the parameters of this second order system. And so there's a couple parameters here that we want. We have this K1 value right here, and then we also have a tau value. So we're just going to concentrate on just this first equation. And if I do it for both heaters, then I'm just going to have a K1 and a K2 and a tau 1 and a tau 2. Okay, so I just have a K1 and K2, and I can also do a K3, which is the interaction between the 2 heaters, and I'll show you how we do that as well. And we'll just have the tau 1, 2. If we assume that those 2 are going to be the same for both heaters 1 and heaters 2, then we can just have one parameter. And so for each of these, I've set a value and then a lower and upper bound. Okay, then I'm going to turn the status on for those, so that means that the solver can estimate them. And then I put in some of my measured inputs. Okay, I had those from right up here from the data source. And then I'm going to tell the optimizer that we want to be able to use these measurements. Okay, so those are going to be inputs into our model. And then we also have our ambient temperature as well. Okay, we'll have some measurements for our model alignment. And this one is going to minimize the error between the simulation and the measurement. Okay, if we have this, the F status on, the status, we're going to use that later for model predictive control. You can turn that on or off. It doesn't really matter in this case. Okay, and then we also have a measurement gap. That's going to be how closely we want to align to our measurements. So we don't want to overfit our model, and we'll give it a little bit of a measurement gap, a deadband, so that we don't try to fit noise of our system. Okay, same thing for temperature 2. And then we'll have some heat transfer between the 2 heaters, and we'll just make some empirical correlations here. So we've just augmented this equation here. Just for the 2 heater case, you have 2 heaters, you're going to want to just augment it with some additional. Okay, so let me go ahead and just erase these things. Okay, so what I did is I basically had a K1, Q1, TH1, okay, and I'll just say that's T1, 2. And then we also have some plus K3, and then this will be the delta T. And so this is my T heater 2 minus T heater 1. Okay, so I just added an additional term. So in empirical identification, if you know there's some interactions there, you can add the structure and then let it estimate those parameters. Okay, and then for my second one, it's basically just like my first one, except I'm just going to go ahead and switch the sign right here to a negative, just because the heat is going the other way. Okay, but the rest of the equation is just the same. I'm just going to do that for heater 2 as well. Okay, let me go ahead and just write that out. And then you could also write it on the other side if you want, like this, and plus K2 Q2, and then this one's going to be minus K3 T heater 2 minus T heater 1. Okay, so there's our second equation. If we had two heaters, we can model this as well. Okay, but these are both first order correlations. And then we're going to use iMode 5, which is moving horizon estimation. And we'll use this is going to be EV type 2, so that's going to be a squared error objective. We can change that to 1 to do an L1 norm with this deadband, utilize that measurement gap. There's a number of nodes that I want for my collocation. And then I'm going to use the IPOpt solver, so I'll set that equal to 3. Then we're going to predict the parameters and the temperatures with this solve command. Next, we'll just go ahead and create a plot, similar to what we did before, but we'll add a grid to it as well. And just create this plot with the measured and the model values. Okay, so these are going to be your model values right here. And then the measurements are the ones that we imported from before. Okay, and then let me go ahead and do the second subplot just with the heater 1 and heater 2. Okay, and then we'll have some optimal values here. Okay, with K1, K2, K3, and tau 1, 2. We'll go ahead and print those out. We print out the new val of those, so those are the new values that are estimated. We'll save the figure and then show it. Okay, so as this is going, I think we can just scroll down here and see how far it is. Okay, so it's at 417. So I think we can run this. We don't have all of our data yet, but it should be enough to, let's see if there's going to be any kind of like conflict with them trying to write to the file at the same time. Okay, but it's collecting that data. We can kind of see how it's progressing because it writes that file every cycle. Okay, so there it goes. It's estimating the parameters. And there you can see it. Okay, so it's not quite done yet. It's still collecting data. You can see how the first order fit is progressing. Okay, and as we get a little bit more data, it'll finish off at 600 seconds, and then we'll be able to get the rest of the data there. Okay, so let's go ahead and just upgrade this now to second order system. We have our 2 heater model and have done this in Gecko. But let's go ahead and just do this in with a second order system as well. I'm going to go a little bit faster through this and just highlight the points that are different from the first order system. Okay, I'll just go ahead and put that to the other view here just so we can see both of them as we're developing it. Okay, I'll make this one a little bit bigger as well, try to match that. Okay, so just the same thing that we're doing with importing the data. Okay, and getting the values in. All of that is the same. And then as we go down, we're going to just add this new parameter. Instead of just tau 1, 2, we're also going to have this tau 3. Okay, and this is going to be a third parameter that we're going to use to for our model. Let me come back here and just highlight this. We're just adding this additional equation right here, this second order system. So what we're doing is effectively saying, we can either do it in this form right here, which is a little bit more compact, or equivalently for an overdamped system, we can use two equations instead. Okay, but what we're doing is we're effectively just taking our temperature control lab, and here is the heater, and then there is the temperature sensor. And what's happening is we see in the data, and if you saw from the fit that we showed earlier, we had our heater steps, and then the temperature was something like that. It did not follow the first order, which does an exponential decay to the new steady state. Okay, it looks more second order, and that just finished collecting the data. So let's just if we take a look at these plots down below, this is with the data that's available online. You can see the first order fit. You can see this very sharp change right here. It says that as soon as the heater goes down, we should start this exponential decay to the new steady state. But that doesn't happen in reality. It kind of comes up. There's a little bit of a delay. It's more smooth. And so I think what's happening there is you have your heater and then your temperature sensor, and there's a little bit of conduction between those two. So by using a second order system, we're effectively saying, here's a temperature 1 of our heater, and here's temperature 1 of our sensor. And so we're going to divide those into 2 zones, and then let our empirical estimation be able to track it with 2 differential equations, not just 1. And so if you're doing it with the 2 heater, that's going to be 4 differential equations in total. Okay, so we have this. There's our measured inputs. Okay, we're going to tell it F status is 1. Those are measured. And then we have these extra states, the temperature of our heater. So I'll make TH1 and TH2. Let me scroll down here on the first order side. So we didn't have any of that in the first order side. We just had these equations, these 2 empirical correlations, first order equations. Okay, and let me go ahead and scroll down a little bit. Okay, a lot of it's the same. And then just when we come to these new empirical correlations, we're just going to have 2 additional ones. Okay, so these are going to be the temperatures of our sensors, and these are going to be the temperatures of our heaters. They're very similar to the first order equations. Same options that we use for both of them, and then we're going to go ahead and solve it, and then create our plots. Okay, so let's see how this does with the second order system versus the first order system. Okay, we saw that maybe the dynamics were just a little bit, there's more of a lag between the heater value and the temperatures changing. So let's see how well this is going to do with our new data. Okay, I'll go ahead and run it. And then we'll get a result that will show us how this is predicting. Okay, and you can see the number of equations and variables there. Okay, it's solved in about 6 seconds over the 10-minute horizon. There you can see our parameters. You can see that this is a little bit more curved now. You can see there's a little bit more of a it's tracking this conduction from the heater to the temperature sensor, and we're tracking that a little bit better. So in empirical model identification, you want to use the right order of the model, the right number of equations. As you use more equations, it gets a little bit slower to calculate. You can see this problem with collocation had about 13,000 variables, and we had 5 unknown parameters. Still solved fairly efficiently, in about 6 seconds. But as you get to larger, higher order identification, that can be just more complex. Takes more CPU power to identify some of these models. Okay, so that's I want to share with you just a couple things. If you felt like the second and first order, you're missing some of the background on those, I just want to give you some resources on that as well. So if you go to the PDC website, this is just a different course, Process Dynamics and Control. And if you look at the first order link there on the right, you can see some of the math behind the first order systems and how we identify these. And then you can also see some information on second order systems and how we can fit these graphically or put them into state space form. Some of the overdamped, critically damped, and underdamped analytical solutions, and some of the other math behind second order systems. So a final thing that you can do on this lab, and there's a couple questions at the bottom of the lab that ask you about these, just to think about, is what other forms could we use to identify this? So there are time series models like ARX, finite impulse response. You also have state space forms that you could identify. And there's a lot of really great identification packages out there that can help you with linear model identification. So, I'd encourage you in this lab, if you have access to some of those tools, go and import this data into those tools and try to identify other models, other empirical models. There's also a GitHub repository. You can go and look at Simulink, MATLAB implementations of this as well. And then the final thing that you might be interested in is, with this lab, is just come down to the moving horizon estimation portion of this. So we are doing this in a batch estimation right now. So if you come down to Temperature Control Lab D, and down at the bottom, here's going to be some code with moving horizon estimation. So we're going to try to identify these models as every time we get an additional piece of data. And so this one will show how this MHE is progressing, in this loop, and it'll generate a real-time plot. We're doing the same thing that we did in this other, model, but we're doing it, one data point at a time. Okay, and then you'll be able to see that. I'll show you an animation of this as well. If you just go back to the Temperature Control Lab C, I believe it shows it here with the hybrid model. It shows how the models are estimated as you go, and you can see the parameter values changing and adapting. So the end goal of these models, the reason why we want to get these parameters, sometimes it's to feed those to a predictive controller. And so we want to be able to adapt the model parameters, especially so we don't have to do a lot of offline batch training, at occasional regular intervals, but you could have the model update automatically as it gets new data or as process conditions change. Okay, I hope you've enjoyed this lab. Up next is going to be the Temperature Control Lab E. We're going to go back to this one is going to be more hybrid model estimation, where we're going to combine some of the system identification methods, the empirical identification methods, with the first principles. We're going to combine those into one. And so that's going to be our next lab, semi-empirical or hybrid model estimation.